All right, we're solving equations today, and there's something I need to remind you about because it could creep in at some point. So I want to show you a problem that we did back in chapter 2. We solved equations with rational parts to them. I didn't show you all my steps, but I'm sure you guys remember we factored over here, and then we multiplied everything in the equation by the same thing, so all of our denominators canceled. You guys remember doing that? And usually we're left with like a linear or quadratic. In this case, it was quadratic. We solved it. We came up with two solutions, but we had to throw one of them out, and that's the main reason I wanted to talk about this. Do you guys remember why we had to throw out this x equals 2? Because what? Because we can't divide by 0, right? Because there's restrictions on parts of our original function. These all have fractions. So now we need to make sure that the domain restrictions hold up, right? This all goes back to domain, which was from chapter 1. If I asked you to look at this and think of it as a function, what's the domain of this function? What's the domain of 2 over x plus 3? Ooh, it's been a while. Write it down on your paper. Don't stare blankly at the screen. Write it down on your paper. 2x over x plus 3. What is the domain of that function? What numbers are you allowed to plug into that function? I'm hoping you wrote down all real numbers except -3. Some of you may have done that in interval notation, negative infinity to -3 and -3 to infinity, and that's awesome if you did that. But the fact is, you can plug anything you want into that piece except for -3, right? Because we can't divide by 0. What's the domain of this piece? If I were to say, what's the domain of this function? Everything except x cannot equal to 2. And what's the domain of this? Well, I'll tell you, it factors into these two factors. So the domain of this ends up being everything except x can't equal 2 or -3. So that's why we had to throw it out, because it didn't fit into the domain of the parts of the original equation. Okay, you guys remember that? Okay, so we're going to be dealing with equations that have exponentials and logs. So we need to keep this in the back of our head that we may have extraneous solutions. So let's first talk about exponentials. If I have an exponential, it's going to be in some format like a times b to the x power. Are there any restrictions on that? What would the domain of the function f of x equals? If a and b follow the rule is that b has to be positive and a can be any real number. Are there any rules about what kind of exponents you can put onto a positive number? Can you put positive exponents onto things? Negative exponents? 0 is okay, right? So there's no rules about it. So the domain for that would be all real numbers, which means we don't have to worry about extraneous solutions when we're dealing with the exponentials. Logs are a different story, though. If I have a function that says f of x equals log base b of x, there are some things that we can't put into that function. What are we not allowed to put into logs? Well, what's the domain of that function, I guess, would be the big question. If you need to go back in your notes and look, we wrote domain and range and all that stuff for logs a while ago. We graphed them. Where was it? Here it is. The domain for this log function is going to be the same for any domain, any log with any base is always going to have the same domain, 0 to infinity. Can't be 0, can't take the log of 0, can't take the log of a negative number. So when we're working today, we got to remember that any equation that has a log in it, we're only going to be talking about x values greater than 0. Or whatever it is that's inside the log needs to be greater than 0. So we may have to toss out some solutions today because of the logs in the originals. Okay, so that's our background knowledge. From here, we're going to have, this is one of those things where you're just going to have to use all of the tools that you have available to you. This is not cookie cutter, step-by-step math. All of these equations are different. They all have different strategies for solving them. As long as you know your exponent rules, your log rules, how to convert between an exponential and a log, and how logs and exponentials can interact with each other as inverses, then you have everything, all the tools that you need. Okay, so if you've been doing your work and making sure that you understand and you've and been learning this stuff long term, then this should be mildly frustrating for you. If you don't know those things, prepare for a very frustrating lesson today. Okay. The thing that makes it mildly frustrating is when you look at a problem, it may not become clear to you right away what to try. I'm going to give you several different strategies. I'll give you examples of each of them. But when you go into your assignment, the problems aren't going to be neatly grouped as these types of problems where you always do the same thing and these type of problems. You're going to have to look at each one individually. Sometimes you're going to have to try something and it's not going to work. And you're going to have to try something different. Okay? But you can get there. Okay, so this is one of those things where you're going to have to be a little persistent at times. The biggest tip that I can give you is when you approach a problem, look for some Algebra 1 type moves you can make to make the problem simpler. A lot of times you're going to see some like really simple Algebra 1 type moves. For example, when I look at this second example here, there is a really simple thing that I could do at the beginning of this problem to make things simple. What would you do in this second one? First thing before you did anything else. We could divide by 5 on both sides. That problem would be way simpler if we did that, wouldn't it? Now, this one, not so much. If I divide it by 27, 27 doesn't go into 81, I don't think. Or does it? I think it does, actually. Hey, look at us. Does it go into 81? Well, that's fantastic. All right, so look for simple things that you can do to make the problem easier at the beginning. And then from there, just try and use the tools that you got. So we will, this bullet list, we're going to see a couple examples for each of these. So, all right, so let's work through this first one. I want us to go back and pretend that we didn't know that 27 went into 81, though. We're going to work this one out kind of a slightly longer way. It will not, this way will not work on the second one, fair warning. All right, so when I look at this, the first thing I notice about this problem, and again, this is just from my experience of having done lots and lots of these types of problems, but when I look at this, I'm looking at the bases, and I see a base of 27. Do you see why I'm calling that a base? It has an exponent on it, right? Exponent 1. I see a base of 1/9 and I see a base of 81. And when I see those numbers, I know that those are all powers of 3. Agreed? Those things are all powers of 3. The fact that they can all be written as a power of the same base makes me think that we could use the matching bases method to do this. So what my goal is going to be, I'm going to have to use my rules of exponents, which hopefully we are experts at. But my goal is to change this into an equation where it says 3 to a power is equal to 3 to a power. If I can do that, wouldn't you guys agree that these two things have to be equal to each other? We can just drop the 3's and we'll have an equation that we can solve, hopefully. Okay, so that's my initial goal, is to make this thing look like 3 to a power equals 3 to a power. So let's start by rewriting each of these things as 3 to a power. So I've got 27. I've got 1/9. I'm going to leave the exponent alone on that, and I've got 81. 27 is 3 to the 3rd power. 1/9 is 3 to the negative 2nd power. And 81 is 3 to the 4th power. All right, well, this is cool. I know that this is a 4 over here. Nice. We need to get this all together as a single base and lose those parentheses. So do your exponent work. Right now, right here, we're at an Algebra 1 level, folks. Alright, so were we able to come up with negative 2x plus 7, or 7 minus 2x? I know from experience that some of you are still going to be struggling with these exponent rules. If that's the case, there is only one way that I know to fix it. That's go back and grind out some practice with exponent rules. Okay, if you need some assistance with that, please let me know. I can get you some practice sets. I'd be happy to sit down with you and go over them again. But it's a simple matter of you need to remind yourself what those exponents rules are and do what it takes so that when you see a problem like this, you can quickly simplify it. Okay, and I will help you with that. Just let me know. All right, so since the bases match, then we don't need them, right? There's only one way for that to be true, and that is if negative 2x plus 7 is equal to 4. So find me an x value that makes that true. Now we're definitely at an Algebra 1 level. All right, and do we need to throw anything out here? There are no logs here. Exponents can be anything we want to, so that should be good to go. All right, let's ask some questions on that. What questions do you have? I got a question for you. What would have happened what if we had divided by 27 at the beginning? Then our equation just would have been 1/9 to the x minus 2 equals 81 divided by 27 is 3. Could we still have used this same process? And would we have gotten the same answer? Yeah, I would say like this already is a base of 3. I would just turn this into 3 to the negative 2. And then use my power to a power rule, multiply that negative 2 times the x and the other negative 2. And we would have gotten to there, which is slightly different from what we had here, but when we drop those bases and solve, we're going to end up getting the same exact solution. So it just would have been a little bit faster if we had caught that and divided. And you guys did catch it. I forced us to go the long way. Sorry. Get your calculators out. Let's talk about how we can check answers to these things. All right, at some point you're going to be assessed on this and you're going to want to know if your answer is correct. More importantly, at some point some of you guys are going to be designing medical devices and bridges and that kind of stuff, and I hope that you'll be checking your work and making sure it's correct as well. So something that we should always keep in the back of our mind, how can we check and make sure that our calculations are correct? Got a couple ways that I've shown you in the past. Do you guys remember any of them? When we're solving an equation, what's the first way you learn to check solving an equation back in Algebra 1? Plug it in, right? That job can be a lot easier for us, though, by doing what? Our calculators will store this value, and then you can just use a variable for it. So if I were going to check this and I wanted to do it quickly, I would just store 3 over 2 into x. And then I'd type in this side of the equation and hope it ends up equaling 81. You do have to make sure you remember when you're typing anything into the calculator with an exponent that has more than one thing in the exponent, it's important to put parentheses around that. Huzzah. The other way I could check this would be graphing it. So I would graph the equation y equals 27 You guys don't have to type this in, but I just want to remind you how you would do this, x minus 2, and then I would get a 0 on one side, so I'd subtract 81 from both sides, so there would be a minus 81. I'd graph it, and then I look for an x-intercept. So get a 0 on one side, graph the other side, you got an x-intercept, and then we can check second calc value. I came up with 3 over 2. If this gives me a 0, then we're good to go. That's it. So just a couple ways that you can check your work. Keep those in mind. Okay, let's do this one. Let's do it the fast way. Actually, I don't think we can do this the same way we did this, because when I look at 5 and 3 and 45, those are not all powers of something, right? There's not a common base there that we could use. So we're kind of stuck dividing here. So go ahead and divide by 5. That's going to get us a base of 3 and a 9. What's our common base here? We can write those both as 3 to a power. You guys finish this one up. So try and rewrite everything as 3 to a power. If you can get the equation to a point where you've got 3 to a power equals 3 to a power, then drop the bases, solve the equation. Hooray! Check this. Uh-oh. Oh, I typed it in wrong. There we go. All right, any questions on that one? Okay, let's go on and see what else we got here. Oh, we're going to do the same equation 3 different times here. This will be fun. So sometimes you're going to have multiple paths to success. So in an equation like this, when I look at this, I see a base of 2 and a base of 17. That last strategy is not going to work for us, right? I can't write 17 as 2 to a power. So we have to think about other ways that we can do it. And one common way, and this is especially when your x is an exponent, is to change this into log form. Okay, we've practiced this. You had a dozen problems like this on a previous assignment. By now, if I give you an equation that's in exponential form, boom, you need to be able to write it in log form. So go ahead and do it. Write this equation in log form. You have done this. You've practiced this. If you need to go back and look at your previous notes, go ahead and do that. I will tell you right now, if you're not able to do this quickly, that should be a red flag for you. That is something you need to be working on. Some of you learned the circle of success last year. I like just using vocabulary. You know what the bases are. You know what the exponent is. That should be enough to get you there. So when I look at this, I say, what's the base? The base is 2. You know where the base goes in a log equation, right? Base goes here. What's the exponent in this equation? Exponent is an x. And a log is an exponent. So the log is an exponent. So the exponent goes there. And then by process of elimination, 17 must go there. And that's pretty convenient, isn't it? It's solved. All we had to do was convert it into a log format. Now I know that x is equal to the log base 2 of 17. Cool. Hey, let's practice here. Can you, without your calculator, can you estimate? Don't shout it out. Write it down on your paper. Can you please estimate the value of the log base 2 of 17? Give me an estimate. Give me a guess. Let's guess to 1 decimal place. We'll see who gets closest. Log base 2 of 17. I'm hopeful that your thought process is, what exponent can I put on a 2 to make it equal to 17? That's what a log is. It's an exponent. Anybody want to make a guess? What do you think? Nobody's going to guess. Be bold. Come on. 2 to what power would be close to 17? Okay, so 4 point what? Or you want to go 3 point something, or you want to go 4 points? Is it bigger than 4, or is it smaller than 4? Bigger than 4, so 4 point what? 4 point what? Give me a guess. It's just a guess. 4.2. Good, good. Let's try it. Let's see it. Do you guys remember how to type that in your calculator? All right, some of you have that whole log base thing in your calculator, but the rest of us can do it, and it's even faster. We just take the log of 17 divided by the log of 2. So this is that good old change of base formula. Ooh, I heard a couple people say 4.1. That'll be a little bit closer. But 4.2, that's a really good guess. That's excellent. All right, let's do this a different way. Another way we can do this problem is we can leverage the fact that logs and exponentials have a couple different relationships that are useful. So, for example, I can cancel this 2, an exponential of 2, if I think of what's the inverse of an exponential with a base of 2. It'll be a log with the same base, right? And you're allowed to do a log with the same base on both sides. So I could rewrite this as the log base 2 of that equals the log base 2 of that. It's not x, it's 2 to the x, sorry. And what happens when you have an inverse and or a function and its inverse and you hook them up back to back? You stick in an x, you're going to get out an x. That's what inverses do. If you hook inverses up together, whatever goes in is what comes out. So that just becomes an x, and then we've got the log base 2 of 17, which we decided was about 4.1. Log base 2 is convenient, but guess what? We don't even have to use the log base 2. We could use any log, and so this is another common way to solve these. So let's do the same thing again, but let's use ln this time. So we just took ln on both sides. It's still 2 to the x and 17. Now this time the ln doesn't cancel the 2, but what are we going to be allowed to do with this x here? It's an exponent on the inside. We have a log rule that says that can become a coefficient on the outside. And if I'm trying to get x by itself, I think we could just divide at this point, right? And we're going to get x equals ln 17 over ln 2. Now, fair warning, I'm not going to be happy with this answer on a test. Okay, and this is what I warned you guys about when I introduced change of base formula. Even though you got a button on your calculator, you still need to be able to use change of base formula. I need you to recognize that this is a change of base formula type equation, right? Or type expression. That is equal to the log base 2 of 17. So an answer like this on the test would earn you most of the credit, but you might miss a point. All right, isn't that cool? You can do the same equation 3 different ways. There's probably another dozen different ways to do that one. Let's see what we can do on this one. Looks like we're going to do this one twice as well. Do you guys see any, like, I'm kind of noticing an algebra move that we could make here to simplify this thing. Are you guys seeing that too? Remember, always, always, always look for those algebra moves that you can do. What could we do? We'll make this, just simplify this thing down a little bit. Yeah, we get rid of that 100. The goal is to get x by itself. So if there's an easy move that you can make by adding, subtracting, multiplying, or dividing, get that stuff out of the way first. So somehow we got to get that x out of the exponent. We got a couple different ways that we could do that. Let's try changing it to a log form. That's an exponential equation. Once again, we are hopefully close to or there already becoming experts with how to take an exponential equation and turn it into a log equation. We've practiced that a bunch. My base is 1.06. My exponent is x. And there we go. Hey, and it's solved. Look at that. That's my favorite way to solve when you have just an x and an exponent. Change it to a log equation, and you're done. We could also use logs to solve this. So if I looked at this and said, I can pull that x out of there if I take a log on both sides. It doesn't matter what type of log I take on both sides. I'm going to do a common log this time. That's going to allow me to bring that x out of the exponent. And then we can just divide to get x by itself. I would like you, though, to, again, change this. We got a log over a log. Rewrite it as a single log to a base. Log base 1.06 of 2. Anybody want to make a guess at that one? That one's a tough one. How many times what's the exponent you'd put on 1.06 to make it equal to 2? I don't know. Any questions on those? I got a question for you, if not. All right, so hey, in a lesson last week, was it last week or was it the week before? You looked at some equations, some functions that look like this. Can you think of a situation where that equation would be used to model a situation? Give me just a second. I want everybody to get a chance to think about this. What were you thinking, Maddox? Okay, interest. So what would the 100 represent in an interest situation? You can open this up to whoever. What do you think? It's a great example. What would the 100 represent? Well, we started, yeah, that's the starting value. We looked at a lot of examples, and this is always where we put the starting value, right? And then we had a multiplier. A multiplier of 1.06 actually tells us something about that interest. What does the 1.06 tell us? We're increasing by 6%, right? This is a 6% interest. And how much are we hoping to get at the end? $200, right? So by solving this equation, we're answering the question, if I started off with $100 at an interest rate of 6%, how long is it going to take me to double it? And if I type this into my calculator, then I would have that answer. And I'm curious, so let's do it. What is the log of 2 over the log of 1.06? 12-ish years. All right. Thanks for humoring me on those kind of questions, guys. I just want to keep us practicing our skills. Okay. All of this stuff is going to come up again next semester, and it's not always going to be separate from each other. So we want to keep practicing things as they come up in context. All right. These problems get a little bit different. Because now our variable is trapped inside of a log. So before we begin this, we talked about domain a minute ago and restrictions. Let's think about the restrictions on this. So if you imagine this part of the equation as its own function, what would the domain of that function be? What would the restriction be? X plus 1 is on the inside, and what's the rule for logs? The thing on the inside of the log must be greater than 0. Yeah, greater than 0, which is exactly what you said. Positive is greater than 0. This is slightly different from square roots. If this was a square root instead of a log, that wouldn't say x plus 1 greater than 0. We just have to make one small change, greater than or equal to 0, because we can take a square root of 0, but we can't take a log of 0. So this should be looking familiar to you from back when we were doing domain with square roots. All right, so if x plus 1 is greater than 0, then x needs to be greater than negative 1. So if we come up with a solution like negative 15, we're going to have to toss it out. That would be extraneous because that can't go into the original equation. All right, we'll keep that in the back of our mind. Let's go ahead and solve this thing. One way to solve these are to change into an exponential form. So just like we did a moment ago, changing an exponential into a log, can you remember how to change a log equation into an exponential equation? Circle of success, or I like to just use the vocabulary. Base goes here. What's the base? Base is 3. The log is equal to an exponent. The exponent is 4. X plus 1 goes over there. Anybody know what 3 to the 4th power is? 81. And then one small simple algebra step gets us to x equals 80. Hooray! Do we need to toss it out? Nope, it fits. It's greater than negative 1. I must have put this here for a reason. There must be another way that we could have solved this. Does anybody have any ideas for another way that we could solve this? Can you think of a way to cancel a log? What cancels a log? What's an inverse of a log? What's the inverse of a log, guys? Exponential is an inverse of a log. So if we did an exponential on each side, this is going to look kind of weird, but we're going to do, and I need to choose the base carefully. What base do I want to use if I want to cancel this log? I better use a base of 3. So if I rewrite this as 3, so log base 3 of x plus 1 equals 3 to the 4th power. That seems like a weird first move, doesn't it? But what's that going to allow us to do? Oh, that 3 and that log base 3 are going to cancel each other out, and you'll just get x plus 1 equals 3 to the 4th. And then you know what's going to happen from there, because we just saw it happen a second ago. So this way I did it changing it to exponential form, and this way we did it by using inverses. All right. Any questions up to this point? You guys are going to love this next part. Oh, this is so cool. Okay. This next thing is super important. But I'm going to tell you that this is probably the first time that you've seen it, and it's going to make your head spin a little bit, okay? And that's okay, because we're going to see it come up. It's going to come up again and again and again. We'll be using this several points in the second semester. And hopefully you're all going on to calculus. You will be using this as a vital strategy next year in calculus, okay? So here's the idea. Okay, I want you to focus on this first equation. This equation's got a lot of stuff going on. We got exponents, and then we got some other stuff going on, but there's something that I notice when I see this equation that jumps out at me right away. There's a certain format of an equation that this thing is following that we've seen earlier. Is anybody else seeing what I'm seeing here? It has nothing to do with the 2 to the x. It's the stuff that's happening outside of the 2 to the x. What are you guys seeing when you look at that equation? Is anybody seeing a quadratic? Does anybody want to see a quadratic equation in there someplace? It's something squared plus something, and then there's some constant. Yeah, are you seeing it now? So we're going to be dealing with equations like this in the second semester where it's going to have, you don't need to write this down, but it'll be like the sine of 3x squared plus 2 times the sine of 3x minus 5 equals 0, right? And you're going to look at that and you're going to be like, what am I going to do? But my hope is that when you see that, you're going to say, oh, that's just a quadratic, right? It's a quadratic with some messy stuff inside of it. So what we're going to do with this, this technique is, this is a psychological technique, by the way. This is not so much math related. We're going to hide the mess of this equation behind another variable. Okay, so we're going to do this thing, and I'm going to use the variable w. For some reason in math, when we do this, a lot of times we use u's and v's and w's. I don't know why. Okay, but we can use whatever we want. The messy part of this, if I wanted to make this look like a quadratic, I want to change this 2 to the x power into something simple, and I'm going to change it into w. So I'm going to say let w equal 2 to the x power. All right. I am only doing this to make it easier for my brain to deal with this problem. This is a strictly psychological thing, okay? Because if I do that, then I can look at this and I can say, okay, then this equation now becomes much simpler. Now it's just w squared plus 2w minus 8 equals 0, and it does not hurt my brain nearly so much to look at this equation as the original one. Right? So I'm just for the sake of my sanity, I'm like, I'm going to hide this 2x behind the w for a little while. And now we've got a simpler equation. We're like, okay, this I can deal with, right? So deal with this. Solve that for me. Spoiler alert, it factors. You could use the quadratic formula, but please factor it. It's much faster. Factor it, then use your zero product property to solve it. All right, we got it. W equals -4, W equals 2. Nice. Okay, and that's great, except we weren't trying to solve for W, we were trying to solve for X. So now that we've simplified things down, and I know that W is equal to each of these things, what we're going to do next is just back substitute. We're going to put this 2x back in for W. I'm going to get an equation 2 to the x equals -4, and 2 to the x equals 2, and then we'll just solve those two equations, and we'll know what x is. That first one's giving me a little bit of pause. Is there an exponent I can stick onto a +2 to make it equal to -4? What do you think? All right, not too sure. Well, what other methods do we have to solve this? We solved a problem pretty similar to this recently, like on a previous page of this notes. We've got several options here. You guys want to turn it into turn it into a log equation? That's one of our options. Let's do that. Try and turn that into a log equation for me. Log base something of something equals something. So you can get all the pieces in the right place. All right, so can we do that? Can we take the log of a negative number? No, so this would be, x would be undefined here, so there is no solution coming out of this. Okay, so my initial question was, is there an exponent I can stick onto a +2 to make it equal to -4? The answer is no. There's no solution here. There is a solution here, though. In fact, we don't need to do any fancy work to do this. What is the exponent I can put on a 2 to make it equal to 2? X equals 1. And that would be our one solution to that. Now, we didn't think about extraneous solutions at the beginning. Was that a mistake, or were we okay there? Is there anything in the original equation that could cause us issues? Square roots, fractions, logs? No, we don't have any restrictions on this, so anything's fine. Okay, what do you guys think about this W substitution? Does it seem really weird to you right now? You're okay with it? We're going to see it come up a bunch of times, okay? And sometimes it's like, why are you changing the variable? The whole idea, though, is when I look at an equation like this, it makes my head kind of hurt. It is possible to factor this thing and keep the 2 to the x power throughout the whole problem. It's complicated. It gets messy, and it's just hard to think through it for me. So when I have something, when I recognize a quadratic or some other format, but there's something weird in place of what I would normally just see as a variable, just take that weird thing and set it equal to a variable and deal with that portion of it first. And then once you get the quadratic solved, go ahead and plug back in the messy piece and use that to solve for x. All right, look at this second one. Oh boy. Does that look like a quadratic to you? Me neither. What I notice about this that's going to make it difficult for us to use any of our previous strategy is that there's two of the same bases, but we have addition here, and I don't have any exponent rules for when I'm adding two different bases. If this had been multiplication, I could put those together into a single base, but there's no rules for when we're adding bases with an exponent. Okay, so this would leave me, again, just strictly based off of my experience, because I'm not going to be able to change this into an exponential, because we don't have a situation with two separate bases. We could take a log base 2 on both sides, but that's not going to do anything. It's not going to cancel both of these. Like, we'd have to do it to the whole side, and once again, we don't have any rules for when we have addition inside of a log. So that's not going to help. Nothing that we've done is going to help, so I'm going to guess that this is a quadratic. It's just in disguise. Okay? So I'm going to see if we can do some work on this to make it look more like a quadratic. Like, for example, that makes it look a little bit more like a quadratic to me. At least we got 3 terms and a 0 on the other side. Can you think of a way to rewrite 2 to the 2x so that it's something squared? That would make it look more like a quadratic. What would I put inside of here so that it'd be equal to 2 to the 2x? How about just 2 to the x, right? And then I'm looking at this and I'm thinking, if this is 2 to the x, that's the thing I'm going to want my w to be. So can I try and rewrite this so that it's got just a 2 to the x, and then how am I going to get that plus 1 in there? What do I do to bases to add things in the exponent? We multiply. So I could multiply 2 to the x times 2 to the 1, right? 2 to the x times 2 to the 1 would give us 2 to the x plus 1. I think we've done it. We have successfully forced this thing into a quadratic looking equation. It's actually the exact same one that we just did a moment ago. So from here, we would just go up here to finish it. So how did I know to do that? Seen a lot of these problems. There's 3 terms. Nothing else that we've tried so far is going to work on it. Let's see if we can make it look like a quadratic. So I want you guys to give this a shot. Could you please follow the same steps that we just did up there with this one? See if you can make it look like a quadratic. Maybe start by getting that -20. See if you can do something so that that ends up on the left-hand side and we got a 0 on the right-hand side. And your ultimate goal is to make it look like something squared plus or minus something times something squared. Spoiler alert, you're going to have a plus 20 equals 0. And then once you get it to there, go ahead and do your W substitution and see if you can solve like we did in that first example on the top of the page. That wouldn't be squared. Just be that. I don't know why I had this squared. I apologize for that. All right, yeah, that does not factor, does it? -5 and 4 don't give you the positive though. If that had been when I was looking at it, I was thinking -5 and +4 also, but we got to get a positive 20 there. So there could be a typo in this problem. If this comes out with imaginary zeros, then we'll just say there's no solution. Let's see. So B is -1. A is 1. C is 20. Oh, gosh. Okay. Shall we modify it so it does factor? You guys want to change the problem, or you just want to say there's no solution? I think there's going to be no solution because I'm going to end up with a negative underneath here, right? And then we're eventually going to have to then take the logs of some imaginary stuff, which we're not getting into what that means in this class. Would you guys be super angry with me if I change this negative 20 into a positive 20? You're okay with that? Oh, I appreciate your grace. Thank you. This is going to make our life so much easier. That's a minus 20, and now it does factor. Way better. Okay. I'm sorry, guys. I'm sorry. All right. Way cleaner now, though. W minus 5W plus 4. All right. If you finish up, I'm going to challenge you to look at that last one. This will be the last problem we tackle today, and the challenge here is going to be that thing's a quadratic. I'm just going to tell you it's a quadratic. Can you make it look like a quadratic? Does anybody have any questions on the one that I had the typo on? Thank you again for being so gracious. Are we able to come up with log base 2 of 5? Someone give me an estimate. What's the log base 2 of 5? What's the exponent you put on a 2 to make it equal to 5? 2 point something, right? What do you want to say? 2.2, 2.3? Which one? 2.3? You're going 2.3? Anybody want to go 2.2? Anybody want to go 2.1? Logs are kind of weird when it's kind of close. Logs kind of skew things downwards. I'm going 2.1. Log of 5 divided by log of 2. We'll see. 2.3. I went the wrong way. Nice job. Nice job. All right, let's look at this last one. I'm just going to tell you this is going to be a quadratic. You're going to have one or two problems in your assignment. They're going to look very similar to this, and those are quadratics too. How do I know that? I see a base that have different exponents, and I can't think of any way to combine them together. So give me some steps we could do to make this look more like a quadratic. What's your first instinct when you approach this problem? Multiply by 3, clear the fractions. That's a great first instinct. If that was what you were thinking, like, hey, there's no reason for us to have fractions here. Let's multiply and get rid of that. That's excellent. That is great mathematical intuition. All right, what's that leave us? 2 to the x minus 2 to the negative x equals 12. Okay, not quite looking like a quadratic to me yet. Quadratic's going to have something squared, and I don't see anything that's squared right now. What's your next intuition? You want to get that 12 on the other side? We know we're eventually going to have to do that, so let's go ahead. Yeah, I think that's a good next move. All right, it's looking a little more like a quadratic, but I still don't see anything squared. I kind of wish that this was like a 2x, right? If this was a 2x, then we could kind of deal with it like we dealt with this one over here, but it's not. What do you think? Any ideas? All right. I don't know that I would have come up with this on my own, but I'll tell you what we're going to do next. Spoiler alert. Sure nobody has any ideas you want to throw out here? Yeah. Oh, did I spoil it? I'm sorry. What were you going to say? Okay, but tell me the partially developed thought, because there's another way to do it than the way I've started up here. So that we have a different base. Hmm. 2 to the something to the something. I get what you're saying. I'm just not sure what to do about the negative. Hang on to that thought. Write yourself a note down, and then I want to try this, and I want to see if we can maybe work backwards towards what you were talking about in a minute, okay? Because I like what you're saying there. I'm going to multiply both sides by something. I'm going to multiply both sides by, anybody want to guess? It's going to have an x in it and a 2. I'm going to multiply both sides by 2 to the x. What's this going to become? What do I do with my exponents when I'm multiplying two bases together? We add them together. What's x plus x? 2x. There's that 2x that I was looking for. Minus, and then I'm multiplying the same base again. What do I do with my exponents when I'm multiplying the same base together? Add them together. What is x plus negative x? All right, for my final trick, I'm going to turn this into a quadratic function. It is 2 to the x squared minus 12 times 2 to the x minus 1 equals 0. Oh, this one's going to be fun because I'm pretty sure that doesn't factor. Practice your quadratic formula skills here. If any of you are keen to do completing a square, you're welcome to do that too. One 44 plus 4, 148. 148's got to have some perfect squares in it. I should have written smaller. I ran out of room. Oh well, that's what scratch paper is for. Please be 4. Yes! All right. All right. I'll give you a chance to ask questions here in a moment. I do want to preview what we got coming up. So just a reminder, our test is in a week and a half. Not next Monday, but the Monday after that. I'll see you guys next Tuesday and Thursday. Those are both going to be review days. I need to do some quick notes on Friday. I know I told you we were going to have a review day, and it will be mostly that. So at least half of the period you'll have to review, but we need to go over compound interest and continuous growth models. Those are both key concepts for your future lives, and they're things that you're going to deal with next year in calculus. So I need to make sure we don't skip over those. And then we'll be reviewing next week. Folks,